What we've been doing is we've been talking about just how to find the derivatives. We can find the derivatives of the functions. Alright? And it doesn't really do us any good to keep finding derivatives of functions. Right? We obviously need to practice that more and more, and you're going to get more practice. But we don't need to just keep practicing. Alright? What the thing is derivatives is very applicable to real life situations. So what we're going to do here is we're going to start looking at how to find or how to apply the derivatives to problems such as like word problems like this. Right? So the first problem that we have is we're going to want to, I would say, break down this problem. Right? Hello? Okay. So it says find the rate of change in the volume of a cube with respect to the side length. And the side has a length of 1 inch, and the side has a length of 6 inches. Right? So, first of all, the first thing that you should see, the first thing that you should understand, is you see the words rate of change. Right? So let's write that in terms of something that we can understand. When we hear rate of change, what does that say that we should be looking for? What are we working with that? Derivatives. So it says find the rate of change. So what that's really saying is find the derivative. Okay? So find the derivative of the volume of a cube with respect to the side length when the side has a length of blah, 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 blah. Now, what we need to do here is this. We need to, first of all, we also need to know something else. What do we possibly need to know here? What do we typically take derivatives of? Not square roots. Not a next one. What we take derivatives of what? Functions. Okay? So we need to know the function for the volume of the cube. So how do we find the volume of the cube? Length times width times height, and what's the cool thing about a cube? All sides is equal to the length is equal to the width, which is equal to the height. So what we can actually say is that the volume is equal to x cubed. We'll say x is the length of the side. Okay? So we have the volume of the cube right here. So it says find the rate of change, or find the derivative of the volume of the cube. Okay? So how do we find the derivative of this? What? First of all, let me ask you this. How do we represent the derivative of this? If it says v equals x cubed, how do we represent the derivative? So dy, so you're saying like dy dx, and that's what we're using. I like that. However, this is a y. So instead of dy, it would be dv. Alright? And that's good. I like this because what it allows us to do is it's going to allow us to figure out what our units are very easily. Alright? So when you're dealing with these types of real world problems, now you can put like v prime if you want. But again, if you write dv over dx, alright, that helps us figure out what our units are going to be. Alright? So first of all, this is how we represent this. So the derivative of the volume, the rate of change of the volume, is equal to what is the derivative of x cubed? Dx squared. Alright. So we've done the hard part. We've found the derivative, we've found the rate of change of the volume of the cube. Now, we just need to find it where the side length is 1 inch and the side length is 6 inches. Alright, so we want to look at 1 inch. Right? The 1 inch, how do we figure that out? You're going to plug in 1, so it'd be 3 times 1 squared, which is equal to 3. Alright? Now, here's the problem. Is, people would be graded an AP test. They may decide they want to be mean to you and take a point off of that. Because that's the right answer, but if we got one big important thing, which would be what? The units. So, what do you think? I think there's going to be an interest in there. There's something else there. Remember how I told you dV over dx is going to help you figure out the units pretty easily? What is the units for volume? Inches cubed. We're going to have inches cubed. What is the derivative for, what is the units for our side of our leg? For the side leg, what is it? Inches. So it's going to be inches cubed over inches. And that's our derivative. And that's our unit. Alright? Now think about what this is saying. It's saying that if you start off with a small cube, and you at 1 inch, alright? What's going to happen is as the cube is changing, alright? For every inch that the side changes, for every inch at the side that changes. So it changes, so the volume is going to increase at a rate of 3 cubic inches per inch. Alright? So if we increase the volume of 2 inches, the volume is going to increase by 3 cubic inches per inch. Alright, so what it's describing is describing how fast the volume is changing. 3. Well, what it's saying is for every inch that the side increases, the volume increases by 3 cubic inches. Alright. So, part B, for 6 inches, here, how do we figure that out? Squared. That's going to equal 36. 36 times 3 is going to be 2. And 8. And that's going to, what are you going to do? What is the n cubed? Inches cubed, or so you say that 108 cubic inches per inch. Alright. Now, does that make sense? So, in some of your homework tonight, you might be asked about cube. U equals x cubed. What are some other common volume or area things we have? What's the area of a circle? You might have to do that. Alright? Well, how would you figure the derivative out? Would be instead of dv, instead of dv would be what? Alright? In this case, actually, it'd be dA. What's my variable? R, so you have dr. Alright? That'd be equal to, so the derivative would be equal to 2 out front. You have 2 times R. Okay. There's another one. You might have like cylinders. All you do is move volume of the cylinder. I doubt actually it's an cylinder. I think it's an the only other one that I see on your homework, so that's a circle. Volume of the cylinder, alright, is 4/3 pi r cubed. Alright, so that's a cylinder. Circle. Not cylinder. Crazy part. Sphere. Alright. So typical spheres and thumbs. Ball, egg, and ball. All right, and talking about how fast is it increasing as we pump it up. All right, so pretty straightforward, right? It says find the rate of change and find the derivative. So we're gonna look at this, and what we're gonna be talking a lot about, all right, something that this type of map deals with and works well with is position functions. All right, so right here, what we're doing is we're gonna look at this example where a ball is going straight up in the air with initial velocity of 40 feet per second and initial height of 10 feet per second. All right, its position is modeled by S&T, right, position, is equal to negative 16 t squared plus 40 t plus 10. So, you don't need to write this right now. So, again, on the graph, so what you're seeing is this represents the position of the ball, right? So on the graph, you saw the ball go up. The ball going up, ball going up, ball going up, ball going up, ball going up. It gets to the top of the path, right? And then it's so the speed is positive, it's going up, all right? And then this represents the position. So then right here, it starts going back down. So then the speed starts decreasing. All right. So both these represent the path of the ball. And what we're going to look at is we want to look at what the derivative of this function does and how that helps us figure out the speed of the ball that we are attacking. All right. So we'll come back and think about that. But we're going to spend a lot of time with position functions. All right. And the natural thing is, when you start talking about position, you want to discuss how fast something is. All right? So this is important. You definitely want to get this stuff down right here with these stars. So as we spend more time with position functions, we become interested in the rate of change of position. All right? So what that tells us, what ends up happening is the derivative of a position function, or a position curve, is the velocity curve. Alright? So the rate of change of position is velocity. So if we take the derivative of position, it gives us the velocity curve. Okay? And then, so as we begin looking at velocity, and maybe you guys take this question. So as you become interested in velocity, you start asking, what about the rate of change in velocity? And again, rate of change means what? What's that mean? The derivative. So as you begin looking at velocity, you start saying to yourself, well, no, we're actually interested in figuring out the rate of change in velocity, which gives us the fact that the derivative of the velocity curve is the acceleration curve. So what we get here is that position, velocity, and acceleration are all related by being derivatives of each other. Right? So the derivative of a position function or position curve would be velocity. The derivative of the velocity curve would be acceleration. So so at that point, what we also get is that the position curve, the second derivative of the position curve is velocity. So what we have here in quick notation I got that down is we get s prime of t equals v of t. Okay? So saying the derivative of the first derivative of position is equal to velocity. Alright? And then what we get, the other thing that we get is that's good, and then the second thing we get is the second derivative of position is equal to the first derivative of velocity, which is equal to acceleration. Alright? So all of these are related. Questions about that? We're going to do a couple of examples and see how it all goes out. So, we have a quick question. What is the difference between speed and velocity? What is the significant difference? Velocity comes along with, it has a direction. Alright? The velocity has a direction. Meaning, the number that you get for velocity, it can be positive or negative. Alright? And a positive velocity means that something is going up or to the right. A negative velocity means something is going down or down or to the left. So, the only difference between that and speed is that speed doesn't have a direction. Okay. So, for instance, let's say that I am driving my car, or let's just say I'm throwing a ball and it's going down. It's going down, so let's say that the velocity is maybe 10 meters per second of the ball. Okay, what this means is that it is moving, so this means that it is moving down 10 meters per second. Okay? So negative means it's going down. So if I throw the ball up in the air, then I say that we find out the velocity is negative 10 meters per second after, let's say, after 3 seconds, then that means that the ball is falling. Okay? Speed would just be 10 meters per second. So it doesn't have a direction. Even if it's going down, the speed would still just be 10 meters per second. Okay? Does that make sense? That sounds good from physics? Yeah? Good. So, let's look at, I believe, an example. So, we have a dense, solid object dropped from rest Well, a that solid object dropped from rest to fall freely near the surface of the earth will follow the position function s equals h0, so the initial height, minus 16 t squared, where t is measured in seconds and s is measured in feet. Okay. So it's asking us to find the velocity of a rock dropped from the top of a 100-foot cliff after its own descent. Okay. So we know that position is so h naught or h sub 0, that's equal to the initial height. So what is the initial height of this object? Where are we dropping? How high are we dropping? 100 feet. So our position function is going to be equal to s equals 100 minus 16 t squared. Okay. We want to figure out the velocity after 1 second. So what do we know about the relationship of velocity to position? What do we know about the relationship between velocity and position? Nope, can't. If I plug in 1 right here, it'll be 100 minus 16, that's going to give you the position. Now, this is the position function. I'm not asking what the position is, I'm asking what is the velocity. So what is the relationship that we just wrote down, that we just talked about, between velocity and position? Velocity does have a direction. That's not telling us anything about the position, but there's a relationship. The derivative of a position curve is a velocity curve. The first derivative of position is equal to velocity. Okay? So, to figure out velocity, we need to find the first derivative. So S prime is equal to, Michelle, what's the derivative of this? That's me 32. Well, what about this 100? So it's going to be negative 32. Okay. Now, we want to find the, so S prime, okay, this is equal to our velocity. We said the first derivative of the position is equal to velocity. So we want to figure out the velocity after 1 second. So what are we going to do now? Well, we want it to which of these functions? So the derivative, so it's going to be S prime of 1 is equal to negative 32 times 1 is equal to negative 32. Now, we need to have the units here. Alright? So, what would the units be? %. And the one way that can help us is we have S, which is our position. We have S is equal to whatever. All right. We could rewrite that as our variables t, so it could be ds dt. All right. Well, how S represents position. So how is position measured? Is measured in feet in this case. All right. How is time measured? Is measured in seconds in this case. So we feet divided by seconds. Feet per second. All right. So if the velocity is negative 32 feet per second, what would the speed be? 32 feet per second. Right? Something that we could jump back real quick. Right here. Alright, so speed equals the absolute value of velocity. Alright. absolute value of the velocity.
Would be for a line that before?
Okay. Alright, so the same rock, alright, same equation for height, same equation for velocity. So it asks, alright, when does the rock hit the ground? Alright, so the rock is going to hit the ground. And you figure that out. How do you figure that out? Let me ask you this: when the rock does hit the ground, how high off the ground is it? 0 feet, right? So we know that when the rock hits the ground, the position of it will be equal to what? 0. I know, right? So it says, so it's going to be S is equal to 0. So it'll be 100 minus 16g squared equals 0. Alright? So, the quick and easy way to figure that out, well, actually, let's see. So you're going to have negative 16g squared plus 100 equals 0. I can factor a negative 2 out of that, so there's negative 2. That's going to be, I can factor 4 out of it. So I'm going to factor the negative 4. That's going to be 4t squared plus 100 divided by 25 minus, let's see, minus 25. Alright? So that's going to equal 0. What happens there then is that's going to return to 2t plus 5 and 2t minus 5. Okay, so I factored that. I set both of those equal to 0. So we do 2t plus 5 equals 0. Subtract 5. 2t equals negative 5. That's going to be t equals negative 5 divided by 2. Divide times b negative 5 halves. I can't have a time that's negative 7. That's not possible. So I know that's irrelevant. We're going to have 2t minus 5 equals 0. Add 5 to both sides. We get 2t equals 5. So t equals 5 halves. Okay? So what happens here, and I'm just going to summarize. This tells us that this rock is going to hit the ground at t equals 5.5 seconds, or 5 half seconds, or 2.5 seconds. And then to find the velocity, you just plug 2.5 in for t. To find the speed, you just take the absolute value of that. So you're going to have velocity equal to 32 times 5 halves. I'm just going to show you guys on the most place. Negative 32 times 5. You negative 80 per second. And the speed will be 80 per second.
You've got the stapler.
Stapler should be up here.